Hi there. Welcome to the Science Lullaby. I'm really glad you're here. Perhaps you're lying in bed, your room dim, your breathing slow. Maybe you're here to quiet your thoughts and let the soft rhythm of science carry you into sleep. Wherever you are, thank you for being here. Tonight, we begin a journey not through oceans or dreams, but through time itself, to a moment before anything existed, before the stars, before the atoms, before even time, before everything. Try to imagine it. A universe without light, without sound, without motion. No galaxies, no particles, no before or after. Not even darkness, because darkness requires space to exist within. Physicists call it a singularity. But that word feels too small for something so absolute. It was not emptiness, it was potential, compressed into a single, impossible instant. Everything that ever would be, every atom in your body, every star, every planet, every sound, was once contained within that singular moment. Then something happened, something that would change everything forever. The universe breathed. The first moment. In that first fraction of a second, a period called the Planck time, just 10 to the minus 43rd seconds long, space began to stretch. Not an explosion into space, but an expansion of space. Imagine a balloon inflating, not into the air, but into existence itself. The energy, locked within that singularity, unfolded into the first dimensions, the first forces, the first heartbeat of reality. Time began to flow. Temperature soared beyond imagination. Matter and energy intertwined in a chaos so perfect it could only be described as balance. A universe of soundless fire. The early universe was pure energy, a sea of light and heat dense enough to erase form. No atoms, no stars, just waves colliding in an endless cosmic symphony. If you could hear it, though sound couldn't yet exist, it might have been like a low, slow hum, a vibration of creation. Some scientists call it the music of the Big Bang. We can still detect its echo today, a faint radiation filling the cosmos, the cosmic microwave background. It's the afterglow of that first light, a whisper from the beginning of time, still traveling through the dark. The dawn of time. From nothing, there was now something, space, energy, possibility. For the first time, the universe could change. It could grow, cool, and evolve. And as it did, laws began to form, not written by a creator, but emerging from the simple fact of being. Gravity began to shape the chaos. Forces separated like colors from a prism, strong, weak, electromagnetic, and gravitational. These forces would sculpt everything that followed, from stars to thoughts, from galaxies to you. The universe expands. As the universe stretched, it cooled. Energy condensed into matter, and the first particles appeared: protons, neutrons, electrons. In those first minutes, the building blocks of everything solidified. But at this point, the universe was still a mist, opaque, glowing, and dense. Light could not yet travel freely. It was a newborn universe, restless, full of motion, but still too young to see itself. The quiet between. Billions of years later, we would give this moment a name: the Big Bang. But that phrase is misleading. It wasn't a bang at all. There was no sound, no center, no explosion. It was expansion, a quiet, everywhere at once unfolding of being. If you could have floated there, you wouldn't have seen fireworks. You would have felt warmth, a diffuse glow of creation, stretching outward in perfect silence. In that silence, time began to count, space began to grow, and the story of everything began. The first light, a promise. Eventually, light would break through, atoms would form, stars would ignite, but not yet. For now, the universe was only beginning to dream of itself. And as we drift through this story tonight, remember, everything you are, everything you've ever known, was once a part of that same instant. You are made of the universe, remembering itself. So close your eyes, let the noise of the day fade away, and feel the expansion, soft, infinite, as time itself awakens. In the next part, we'll linger in that impossible moment before creation, exploring what it means to say there was nothing. This is the nothing that was. Before time began, before even the faintest vibration, there was nothing. Not the kind of nothing we experience, not quiet, not darkness, not even emptiness, because all those things require something: space, silence, light, absence. But before the universe, there was not even that. This is the part of the story where our language fails. We are creatures born inside time, so to speak. To speak of before time is to step outside the limits of thought. And yet, the universe began exactly there, in a place that was not a place, in a moment that was not a moment. The limits of understanding. Physicists and philosophers have tried for centuries to describe this nothing. Some say it was a quantum vacuum, a sea of potential energy fluctuating without matter or form. Others say it was pure mathematical possibility, the rules of physics waiting to express themselves. And some say it was truly nothing. No time, no energy, no potential at all. But even that definition collapses on itself because the instant you name nothing, you've already turned it into something. Maybe the question isn't what came before, but whether before even exists. The quantum whisper. According to modern cosmology, what we think of as nothing may not be empty at all. In the subatomic world, even the quietest vacuum teems with invisible motion, particles and antiparticles flickering into existence and then disappearing again in less than a blink. This is called quantum fluctuation. Energy can briefly borrow from nothingness, so long as it gives it back in an instant so small that the laws of physics can't tell the difference. Some theories suggest that our universe itself may have been born from one of these quantum whispers, a random fluctuation that became stable enough to last forever. A ripple in nothing that became everything. The paradox of nothingness. Think of it this way. If nothing truly existed, there would be no reason for it to remain that way. Nothing is unstable. Like a still pond waiting for a single drop, even the tiniest disturbance can set creation in motion. Perhaps the laws of nature, symmetry, balance, cause and effect, were always there, not as things, but as truths so fundamental that they didn't need to be created. And maybe, inevitably, those laws gave rise to their first expression, existence. From the potential of nothing, the seed of something emerged. The human side of nothing. We often imagine nothingness as frightening, a void, a blank, a silence too deep to face. But maybe it isn't absence at all. Maybe it's peace. The kind of stillness that exists before a heartbeat, before a thought, before a dream. The universe, in that sense, began the way we fall asleep, a slow surrender from noise to quiet, from chaos to calm, and from that calm, a spark was born, the breath before creation. Imagine the entire universe compressed into something smaller than a grain of dust, hotter than imagination, denser than definition. There, within that singularity, the laws of physics existed as potential, like the breath you hold before speaking. And then, in one impossible instant, the breath was released, not into the air, but into time. That first breath was the beginning of everything: space, energy, matter, and the endless unfolding of cause and effect. In that moment, the universe became aware. not in thought, but in being. The birth of possibility. With the first expansion, possibility itself was born. Every galaxy, every star, every life that would ever exist was contained in that first wave of energy. The math of reality, gravity, electromagnetism, motion, all crystallized from nothing as naturally as water freezing into ice. Creation wasn't an act of will, it was an act of inevitability. Given enough time, even nothing gives birth to something. Silence that speaks. When astronomers look into deep space, they aren't just looking across distance, they're looking back in time. Every photon that reaches their telescopes is a messenger from the past, traveling for billions of years. The faint background glow we detect today is not just radiation. It's the echo of creation itself, a whisper from that first silence, still moving through space like the memory of a dream. That silence was not empty. It was full, with potential, with meaning, with everything that would ever be. Nothing and everything. When we speak of the beginning, we imagine a boundary, a before and an after. But maybe there was never a boundary at all. Maybe the universe didn't start. Maybe it was always becoming. Like a song that rises from silence but never truly begins, only continues in new forms. Nothing and everything, not opposites, but reflections of each other. The universe needed both, the quiet and the sound, the void and the spark, to exist at all, the calm before time. And so, before time flowed, there was stillness. Before light, darkness waiting to glow. Before creation, a pause, a sacred breath of balance. You can feel it, even now, between your own breaths. The tiny, weightless moment where everything is still. That pause is the echo of the beginning, the memory of nothing that lives inside every living thing. Because in that first moment, when nothing became everything, the universe left a trace of itself within us, a calmness that never disappears. In the next part, we'll watch that stillness awaken as time begins to flow and the universe takes its first measurable breath. This is the birth of time. What does it mean for time to begin? It's a question that seems simple until you try to answer it. Because before time, there was no before. No ticking, no sequence, no cause and effect. And yet, in a single moment smaller than imagination, time began to flow, and with it, everything else. The first second. The first instant of existence is called the Planck time, 10 to the minus 43 seconds after the Big Bang. Before this, physics as we know it breaks down. Our equations cannot describe it, our language cannot express it. But from that unthinkably brief moment onward, time became measurable. Events could happen. The universe had direction. This was the birth of history, not human history, but cosmic history itself. The expansion of time. As space stretched, so did time. You can't separate them. They're part of the same fabric, woven together into what Einstein called space-time. Imagine a sheet being pulled in every direction. That's what the universe was doing in those first seconds. Every point of space moving away from every other, carrying time with it. As space grew, so did the interval between events. A second began to mean something. From that moment on, the universe would never stop moving forward. The arrow of time. We often talk about the arrow of time, the idea that it moves in one direction, forward. We remember the past, not the future. We grow older, never younger. A glass can fall and break, but the pieces never leap back together. This direction comes from entropy, the gradual spread of energy, the universe's natural tendency toward disorder. In the first instant, entropy was almost zero, everything perfectly ordered. But as the universe expanded, chaos increased, and with it, time found its flow. So when we say time began, what we really mean is that change began, the universe's quiet drift from simplicity to complexity, gravity and the shaping of time. Einstein showed us something profound. Time isn't absolute. It bends. Where there is mass, there is gravity. And where there is gravity, time slows. A clock near a black hole ticks slower than one on Earth. Your head is aging slightly faster than your feet right now. That's how sensitive time is to the structure of space. At the beginning, when everything was compressed into a single point, gravity was infinite. Time itself was almost frozen. Then, as the universe expanded and cooled, time began to move freely. The universe learns to count. As the first second stretched into the first minute, the universe was learning rhythm. Protons and neutrons began to form, then fuse into light elements. The cosmos became a kind of vast pulsing organism, its heartbeat marked by reactions, collisions, and the steady cooling of light. For the first time, the universe had a timeline. It wasn't aware of itself, but it was unfolding, moment by moment, like a song beginning its first verse. Time as a creation of change. We often think of time as a river flowing independently of everything else. But perhaps it's more accurate to say that time is change. Without change, there is no time. Without motion, there is no before or after. In the stillness before the Big Bang, nothing moved. And without motion, there was no way to measure anything at all. The instant the universe began to expand, change was born, and time flowed with it, like a shadow following light. The human perception of time. Billions of years later, that same cosmic rhythm lives within us. Your heartbeat, your breath, your thoughts, each follows a pattern set in motion by the same laws. The universe measures time in radiation and decay. We measure it in memories. To exist is to be aware of time passing. To live is to move through it gracefully. And just like the stars, we burn, shine, fade, and in that cycle, we echo the birth of time itself. The slow expansion. As the early universe expanded, it began to cool rapidly, from unimaginable heat to temperatures where atoms could someday form. It's hard to comprehend just how much was happening in those first few seconds. Energy condensed into particles, forces separated, gravity, electromagnetism, the strong and weak nuclear forces. Each split was another note in the universe's opening symphony. And all of it happened within the first minute of existence. The universe wasn't simply expanding in space, it was expanding in time. Every new moment was a new possibility, the mystery of before. Even now, scientists can describe the first second of existence with astonishing precision, but what came before remains beyond reach. Was the universe born from another? Did time itself loop, like a circle instead of a line? Or was there truly a beginning, a first moment from absolute nothingness? No one knows. But in that mystery lies something beautiful. The awareness that we live inside a question still unfolding. The quiet realization. As we move through our gaze, we rarely notice it. The flow of time, the expansion of existence. But in every second that passes, the universe grows. Every moment adds to the length of time that has existed since the beginning. You are part of that growth, a conscious fragment of the universe, experiencing its own unfolding. In your breath, in your heartbeat, in your dreams, time continues to be born. The eternal present. Physicists often say that the past, present, and future all exist at once, that time is not a river, but a landscape. We move through it like travelers walking across terrain, seeing one view at a time. In that sense, the universe didn't just begin, it is beginning, right now, in every instant that passes. Every breath you take is part of the same unfolding that started 13.8 billion years ago. Time never stopped being born. In the next part, we'll watch the first light fill that newborn universe, when energy became visible and the cosmos began to glow. This is the light appears. For hundreds of thousands of years after the Big Bang, the universe was shrouded in light, but not the kind of light that could be seen. It was too dense, too hot, too chaotic. Photons, particles of light, were constantly colliding with matter, bouncing endlessly in every direction. The universe was glowing, but blind. And then, after an eternity of darkness and fire, something extraordinary happened. The light found its freedom. The cooling of the cosmos. As the universe expanded, its heat began to fade. From 1 trillion degrees to a few thousand, still hotter than any star today, but cool enough for atoms to form. Hydrogen and helium, the simplest elements, captured wandering electrons, locking them into stable orbits. For the first time, matter could exist without being torn apart by energy. And when that happened, light could finally travel. The universe becomes transparent. Before this moment, space was like fog, thick with energy and motion. Every photon collided again and again, unable to move freely. But as atoms formed, that fog began to clear. Light could now pass through space without being scattered. The universe became transparent. This moment is known as recombination, and it marks the birth of the first visible light. The same light still fills the universe today, stretched, cooled, and softened by billions of years of expansion. We call it the cosmic microwave background, the afterglow of creation. It is the oldest light in existence, a snapshot of the universe when it was only 380,000 years old, a silent sunrise. If you could have stood there, though there was no there yet, you wouldn't have seen a sunrise. You would have been inside it. A glowing, expanding sea of amber light, soft and uniform, stretching across every direction. There were no stars yet, no galaxies, only light itself, gentle and endless. It was the universe's first dawn, a moment of breathtaking calm after unimaginable chaos. The color of the beginning. That ancient light wasn't white or yellow. It was a deep orange-red glow, the color of heat fading into rest. As space stretched over billions of years, that glow cooled and stretched too, its wavelength becoming longer, its energy softer. Now it's invisible to our eyes, a faint microwave hum permeating every corner of existence. If you could tune a radio between stations, that static hiss you hear is a trace of that ancient light. You are hearing the echo of the first photons, still whispering through space. the message of the light. When scientists mapped this faint radiation, they discovered something remarkable. Tiny ripples, barely perceptible differences in temperature, 1 part in 100,000. Those tiny imperfections would become everything, the seeds of galaxies, stars, and planets. Without those ripples, gravity would have had nothing to shape. The universe would have remained a featureless cloud of light. In other words, imperfection made creation possible. The light wasn't uniform, and because of that, it could grow. The stillness between waves. Even now, that light travels in every direction, through every galaxy, through you. Every photon you see, every spark, every flame or star is a continuation of that first light. When you close your eyes and feel warmth on your skin, you are feeling the same energy that was born in the beginning. The light never went away. It simply changed form. The calm after chaos. For hundreds of thousands of years, the universe remained simple. A tranquil ocean of hydrogen and helium, slowly expanding, quietly cooling. There were no stars yet, no life, no color or form. But within that stillness was all the potential for what would come. It was the first peace the cosmos had ever known. And in that peace, gravity began to work its magic. Tiny variations in density pulled matter together ever so gently. The first structures were beginning to take shape. The Symphony of Light. Scientists often describe the early universe as a kind of music, oscillations, vibrations, waves of density and heat. It's not a metaphor. Those ripples were real, sound waves moving through plasma, carving invisible patterns into the cosmos. If you could translate them into sound, they would form a deep, steady hum, a cosmic note resonating across eternity. That hum is the rhythm on which everything else was built. It's the pulse of creation, still echoing faintly in every atom. The universe looks back. Billions of years later, we built machines to listen to that light, to capture its ancient glow and read its story. The data told us this. The universe has been expanding since that first moment of light, and it's still expanding now. In that light, we see ourselves, our past, our beginning. Every observation of it is a form of remembering, a way of looking backward through time itself. The dawn completed. When the first light filled the cosmos, the universe wasn't yet awake, but it was no longer dreaming. It had taken its first breath, its first step toward complexity. That soft, glowing ocean would one day give rise to stars, and stars would give rise to life. Light was both the messenger and the message. It said, "I am here. I have begun." The light within you. That same light exists inside you, not metaphorically, but physically. The atoms in your body were formed by the fusion of stars, which were formed from the hydrogen of that first light. You are, quite literally, made of ancient photons recycled through time. You are a continuation of the universe's first dawn. Every cell in you is a small memory of that moment when light appeared and the cosmos opened its eyes. In the next part, the universe begins to build its first ingredients, simple elements that would one day make stars, planets, and life itself. This is the first elements. The universe was still young, barely 3 minutes old, but in that brief time, something miraculous had begun. Out of pure energy, matter was forming. The chaos of creation was cooling, slowing, and starting to organize itself. The first ingredients of everything were about to appear. The cosmic kitchen. Imagine the early universe as a vast, glowing ocean, hot, dense, and alive with motion. Inside this cosmic sea, particles collided and combined in an endless dance of creation and destruction. Protons and neutrons, the building blocks of matter, joined together under the extreme pressure. Some fused into helium, some into tiny traces of lithium, while most remained as simple hydrogen. These were the first elements, the foundation stones of all that would follow. Every atom in your body, every star, every planet can trace its ancestry to that brief, shining moment when the universe learned to build. The first 3 minutes. The process was fast, breathtakingly so. Between 1 second and 3 minutes after the Big Bang, the universe's temperature dropped from 10 billion degrees to 1 billion. That tiny cooling made all the difference. At that temperature, protons and neutrons could link together without immediately being torn apart. This process is called Big Bang nucleosynthesis, the birth of the first atomic nuclei. It was chemistry before chemistry, a symphony of simplicity played in the key of creation. Hydrogen, the element of beginnings. Hydrogen, the simplest of all, was the universe's first child. Just one proton, one electron. But it would go on to become everything. The fuel for stars, the source of light, the essence of water, and the breath of life. Even now, after 13.8 billion years, hydrogen still makes up most of the universe. Every flame, every star in the night sky is hydrogen remembering its first moment of being. Helium, the gentle light. As the universe expanded and cooled further, Some hydrogen fused into helium. Each atom of helium was the result of energy slowing down enough to take form. It was gentle, stable, peaceful, a kind of cosmic rest after chaos. The early universe glowed softly with helium's birth, its light delicate and pure, like the color of a sunrise seen for the first time. Helium would become the second note in the melody of existence, the first sign that the cosmos could create harmony. Lithium, the rare whisper. Among the early reactions, a few atoms of lithium appeared, fragile, short-lived, a whisper compared to the ocean of hydrogen and helium. But even that trace mattered. In time, lithium would become essential for the chemistry of stars and planets, and later for the delicate workings of life. Every spark of electricity, every neural impulse in your brain depends on the same elemental dance that began in those first minutes. The balance of forces. The creation of elements was a battle of balance. Too much expansion and the universe would cool too quickly. Matter would never form. Too much density and gravity would pull it all back together, a collapse before life could begin. But somehow, the balance was perfect. Just the right density, just the right heat, just the right pace. A harmony so precise that even a difference of 1 part in a million would have ended everything before it started. The universe, it seems, was tuned for creation. The music of matter. As particles combined, they released bursts of energy, brief flashes of light that rippled through the newborn cosmos. It was as though the universe was exhaling after holding its breath, and in that exhale, the structure of everything was encoded. Every pattern of matter we see today, from the spiral arms of galaxies to the atoms in your skin, is a direct echo of those first nuclear reactions. Matter became music, and the song has never stopped. The long cooling. After the first few minutes, the universe had created all the elements it could. It was still too hot for heavier atoms to form. Carbon, oxygen, and iron would come much later, forged in the hearts of stars that did not yet exist. For now, the cosmos settled into stillness again, a quiet hydrogen-helium mist drifting through infinite space. The first chapter of creation was complete. A universe at peace. It's easy to imagine this time as empty or lifeless, but it wasn't. It was full of potential, full of quiet purpose. Every particle was in its place, waiting for gravity's gentle pull to bring them together again. The next act of creation would not come for hundreds of millions of years. But the foundation was there, simple, beautiful, inevitable. The universe was ready to dream again. The first elements within you. Billions of years later, those same atoms would find each other inside stars, inside planets, inside life itself. The hydrogen that burns in the sun is the same hydrogen that formed in those first minutes. The helium in your lungs, the lithium in your cells, the elements that make you, all of them were forged in that first cosmic heartbeat. When you breathe, you're breathing the memory of the beginning. When you look at the stars, you're seeing yourself in another form. In the next part, we'll drift into the long silence that followed when the universe went dark once again, waiting for its first stars to be born. This is the Dark Ages. The light had faded. The universe, once a glowing sea of energy, was now calm, cool, and dark. This was not darkness as we know it, not shadow, not night, but the absence of light entirely. The first elements drifted silently through space, a vast cloud of hydrogen and helium stretching endlessly in every direction. The fire of creation had gone quiet, and for the first time, the universe rested. The Great Silence. From the moment light became free to the birth of the first stars, hundreds of millions of years would pass. We call this time the Cosmic Dark Ages. There were no stars, no galaxies, no points of brightness in the void. Just invisible matter floating in the quiet aftermath of creation. It was an age of stillness, a time when the universe inhaled deeply, waiting for its next exhale of light. The expanding calm. Though it seemed silent, the universe was far from empty. Space continued to expand, carrying those first atoms outward, stretching them thinner and thinner. Tiny fluctuations, the faint ripples imprinted in the cosmic background, were now growing stronger, slowly pulling matter together under gravity's hand. It was a long and patient process. The universe was learning how to build again, but this time it would take its time. The invisible architects. While ordinary matter drifted freely, another kind of matter, unseen, silent, but powerful, was already shaping the future. Dark matter. It did not shine or absorb light. It passed through everything, invisible and undetectable except through its gravity. Dark matter began to gather into invisible clumps, the scaffolding of the cosmos. Hydrogen and helium gas slowly fell into these gravitational wells, collecting, condensing, and forming the first structures that would one day ignite into stars. The architecture of the universe was being built in shadow. The temperature of nothing. By this time, the universe had cooled to just a few dozen degrees above absolute zero. Cold enough for atoms to move slowly, but not yet close enough to touch. It was a vast, diffuse mist spread so thin that a single cubic meter of space contained only a few atoms. Yet in that emptiness, everything waited, quietly, patiently, for gravity to do its work. Creation was not finished. It was simply paused. The first gathering. Over millions of years, the invisible structures grew denser. Gas began to fall inward, collapsing into tight knots. Each collapse released energy, tiny bursts of heat and light deep within the darkness. These were the first sparks of what would become stars. But the universe was still too cool, too spread out, for them to ignite fully. The stage was being set, but the curtain had not yet lifted. The universe learns patience. For hundreds of millions of years, the cosmos remained in this state, still, silent, expanding. Time itself stretched lazily, measured only by the slow dance of matter, gathering, colliding, drifting apart again. It was a kind of meditation, a universal stillness before the next great act. The universe was learning balance, learning rhythm. Every motion, every gravitational pull was a step toward complexity. The seeds of light. Eventually, deep within those gathering clouds, density reached a tipping point. Hydrogen atoms collided with such force that they began to fuse, releasing light once more. The first stars were about to be born. Their light would pierce the darkness, ending the long night of the universe. But in this moment, that dawn was still a promise. The seeds had been planted. The stars were only beginning to stir. Echoes in the void. Scientists believe we can still detect the faint echoes of this silent time, subtle distortions in the background radiation, a record of the darkness before the dawn. It's strange to think that even silence leaves a mark. Every period of stillness carries the memory of what came before and the potential of what comes next. The universe remembers its quiet phases, and perhaps so do we. The poetry of waiting. If creation were a story, this would be its pause between chapters. No light, no sound, no movement visible to the eye. And yet, beneath the surface, a slow, beautiful transformation was unfolding. It reminds us that even in stillness, things are happening. Growth can be invisible. Becoming takes time. The universe knew how to wait, and in that waiting, it became ready to shine again. The dawn approaches. Slowly, gravity gathered the scattered hydrogen into massive clouds. The pressure within these clouds rose, and so did the heat. At the heart of each cloud, a single spark waited to ignite. Soon, one of them would reach the temperature for nuclear fusion. When that happened, the long night would end, and for the first time since the beginning, the universe would glow again. The lesson of the dark. The Dark Ages remind us that even the universe needs silence, that light means little without the darkness that comes before. It was in the quiet that matter found its shape, that gravity built the scaffolding of the cosmos, that the next miracle prepared itself in secret. Creation is not always loud. Sometimes it happens quietly, in the dark. In the next part, the first stars awaken, igniting light across the cosmos and ending the universe's long night. This is The First Stars Ignite. Hundreds of millions of years after the Big Bang, the universe was still dark. It was filled mostly with hydrogen and helium gas, cold, thin, and invisible. There were no stars yet, no light, and no color. Over time, gravity began to change that silence. It slowly pulled hydrogen atoms together, forming massive clouds across space. As these clouds collapsed under their own weight, the temperature at their centers began to rise. When the heat reached about 10 million degrees Kelvin, hydrogen atoms started to fuse into helium. That process, called nuclear fusion, released enormous amounts of energy. The first stars were born. These first-generation stars are known as population 3 stars. They were much larger and hotter than the stars we see today, some hundreds of times the mass of the Sun. Because of their size, they burned their fuel extremely fast and lived only a few million years. Despite their short lives, they completely transformed the universe. Each fusion reaction inside them produced heavier elements: carbon, nitrogen, oxygen, and iron. When these stars died in violent supernova explosions, they scattered those new elements into space. That material later became part of new stars, planets, and eventually living organisms. In other words, the first stars created the chemistry that made life possible. Their light also changed the universe itself. Until this point, the hydrogen gas in space absorbed most radiation, keeping everything dark. But the ultraviolet light from the first stars began to ionize the hydrogen, breaking its atoms apart and allowing light to travel freely again. This process is called cosmic reionization. It ended the universe's dark ages and made space transparent for the first time in hundreds of millions of years. From that moment on, the universe was filled with light. The energy released by these first stars shaped everything that came after. Their radiation heated surrounding gas, preventing new stars from forming nearby for a while. This created a rhythm, a cosmic balance between creation and rest. As more stars formed and died, the ejected elements collected into new clouds. Each new generation of stars contained more metals and lived longer, cooler lives than the first. This gradual enrichment led to the diversity of stars and planets we see today. Some of the massive population 3 stars didn't explode. Instead, their cores collapsed directly into black holes. These early black holes might have merged over time, forming the supermassive black holes we now find at the centers of galaxies. So, in a sense, the first stars not only created the ingredients for life, they also created the gravitational anchors for entire galaxies. The period that followed is sometimes called the cosmic dawn. It marks the universe's transition from simplicity to structure, from darkness to complexity. Light began to fill space, and with it came the first galaxies, small groups of stars held together by gravity. From then on, the universe was no longer quiet or empty. It had rhythm, energy, and color. The cosmos had finally learned how to shine. In the next part, we'll follow those stars through their full life cycle, from their birth in gas clouds to their explosive deaths that shaped the universe. This is the life and death of stars. Stars are not eternal. They are born, they live, and eventually they die, each one following the same fundamental cycle shaped by physics. The life of every star begins in a molecular cloud, a cold, dense region of gas and dust floating between the stars. When gravity overcomes internal pressure, a part of this cloud collapses inward, forming a protostar. As the gas continues to fall, the temperature and pressure in the core rise. When the core becomes hot enough, around 10 million Kelvin, hydrogen atoms begin to fuse into helium. This is the beginning of a star's life, the main sequence. Once nuclear fusion begins, the star enters the main sequence phase, the longest and most stable period of its life. Our Sun is a typical main sequence star. During this time, a delicate balance forms between 2 opposing forces, gravity pulling inward and fusion pushing outward. As long as hydrogen continues to fuse in the core, the star remains stable. Small stars burn their fuel slowly and can live for tens of billions of years. Massive stars, however, consume their hydrogen rapidly, shining much brighter but living much shorter lives, sometimes only a few million years. Energy and color. A star's mass determines nearly everything about it: its size, temperature, brightness, and lifespan. Small, cool stars emit a soft red light. Larger, hotter ones glow blue or white. The color of a star is a direct reflection of its surface temperature. The hotter the surface, the bluer the light. Even in their differences, all stars are doing the same thing, turning hydrogen into helium and releasing energy as light and heat. That energy is what makes life possible. Every ray of sunlight, every flicker of warmth on Earth is energy released by fusion in the sun's core. The end of the hydrogen era. Eventually, the hydrogen in a star's core runs out. Without fuel, fusion slows down, and the delicate balance between pressure and gravity breaks. Gravity begins to win. The core contracts and heats up again, while the outer layers expand and cool. The star becomes a red giant if it's small, or a supergiant if it's massive. Inside the core, new fusion processes begin. Helium fuses into carbon and oxygen, and in very massive stars, even heavier elements begin to form. This is where the universe starts creating the materials that make up planets, metals, and life itself. The death of small stars. When small stars, like our Sun, reach the end of their fuel, they cannot generate enough pressure to continue fusion. The outer layers drift away into space, forming beautiful glowing clouds called planetary nebula. At the center, the remaining core becomes a white dwarf, a dense, Earth-sized remnant made mostly of carbon and oxygen. Over billions of years, the white dwarf cools slowly, fading into darkness. This is a quiet, gentle death. The death of massive stars. For massive stars, the ending is far more dramatic. When their fuel runs out, gravity causes the core to collapse violently. Temperatures soar to billions of degrees. The collapse triggers a supernova explosion, one of the most powerful events in the universe. In that instant, the star releases more energy than our Sun will produce in its entire lifetime. The explosion scatters heavy elements like gold, silver, and uranium into space, materials that will later form planets, oceans, and living beings. The outer layers are blasted away, but what remains at the center depends on the star's mass. Neutron stars and black holes. If the remaining core is between 1.4 and 3 times the mass of the Sun, it collapses into a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. If the core is even more massive, not even light can escape its gravity. It becomes a black hole, a region of space where gravity is absolute and time itself slows to a stop. Some of these early black holes may have merged over billions of years to form the supermassive black holes that sit at the centers of galaxies today, recycling the universe. Every time a star dies, it releases the elements it created into space. These elements mix with surrounding gas and dust, forming new molecular clouds. From those clouds, new stars are born. This is called stellar recycling, a continuous cycle of creation and destruction that has shaped the universe for over 13 billion years. The carbon in your body, the iron in your blood, the calcium in your bones, all of it was created inside a star that lived and died long before the sun existed. We are, quite literally, the products of stellar evolution. The bigger picture. The life cycle of stars doesn't just illuminate the night sky. It defines how the universe evolves. Without stars, there would be no light, no chemistry, and no structure. They are the engines of creation, forging matter, radiating energy, and connecting everything through gravity and time. Every star is a chapter in the same cosmic story, each one burning so that something new can exist after it. In the next part, we'll see how gravity and time work together to shape the largest structures in existence, from galaxies to the invisible web of dark matter holding them together. This is the birth of galaxies. After the first generation of stars lived and died, the universe changed forever. Those stars filled space with new elements: carbon, oxygen, iron, and many others. The explosions of their deaths sent shock waves through surrounding gas, triggering new waves of star formation. This process slowly began to connect the stars together under the pull of gravity. Over time, those groups of stars became the first galaxies. In the early universe, gravity was the dominant force shaping everything. Even though matter was spread thinly across space, regions with slightly higher density attracted more material. As they grew heavier, their gravity increased, pulling in even more gas and dark matter. These regions became the first gravitational wells, the seeds of galaxies. Most galaxies began small, only a few thousand light years across. They merged frequently, colliding and combining to form larger structures. Each merger released enormous energy, distorting the shapes of the galaxies and triggering bursts of star formation. Over billions of years, these collisions created the spiral and elliptical galaxies we see today. Inside each young galaxy, countless stars lived and died in rapid succession. Their explosions enriched the surrounding gas with heavier elements, allowing new generations of stars to form with more complex chemistry. Planets, rocky surfaces, and eventually life would become possible only because galaxies recycled this material over and over again. At the centers of most galaxies, something even more powerful was forming. When the most massive early stars collapsed, they left behind black holes. As galaxies merged and grew, these black holes also combined, feeding on gas and dust and becoming larger. Many scientists believe that these early black holes became the supermassive ones that anchor galaxies today, including the one at the center of the Milky Way. The formation of galaxies also brought order to the universe. For the first time, matter wasn't just scattered, it had structure. Light now came not from isolated stars, but from vast systems containing billions of them. Each galaxy became a kind of city of stars, orbiting in balance, connected by gravity and time. As the universe aged, galaxies continued to evolve. Some, like our Milky Way, grew into large spirals with beautiful rotating arms. Others became dense, elliptical clusters where star formation nearly stopped. The differences depended on environment, how often they collided, how much gas they had, and how their dark matter halos shaped their growth. Even now, billions of years later, galaxies continue to move, interact, and merge. The universe is still building, still changing, still forming new structures from the remnants of the old. When you look at the night sky, every point of light belongs to a galaxy like this, each one containing its own history of birth, death, and rebirth. We can map ancient riverbeds, trace the outlines of cities, and even recover artifacts untouched by air for millennia. Each discovery bridges science and story, proving that imagination often leads the way. Because before we find, we must first believe that something is there to be found. The meaning of what's lost. Why are we so drawn to lost cities? Perhaps because they mirror us, our fragility, our ambition, our impermanence. They remind us that all things change, that even the strongest civilizations can vanish, and that what endures is not stone or power, but curiosity. As long as we keep searching, Atlantis still lives, not as a place, but as an idea, the eternal desire to understand what lies beneath. The light we see comes from ordinary matter, atoms that make up everything we can touch and measure. But this ordinary matter accounts for less than 5% of the total content of the universe. The rest is something we cannot see, something that does not emit or absorb light, yet shapes everything through its gravity. We call it dark matter and dark energy. The first evidence for dark matter appeared when astronomers studied the rotation of galaxies. They found that stars at the outer edges of galaxies were moving far too fast to be held together by visible matter alone. If only normal matter existed, those galaxies would have flown apart long ago. Something unseen was adding extra gravity, keeping them intact. This hidden mass became known as dark matter. Scientists believe that dark matter makes up about 27% of the universe. It does not interact with light, and it passes through normal matter almost without resistance. We cannot see it directly, but we can detect its effects everywhere. Its gravity pulls galaxies together, shapes their movement, and forms the cosmic web, a vast structure of filaments connecting clusters of galaxies across billions of light years. Without dark matter, galaxies might never have formed at all. In the early universe, normal matter was still too hot and energetic to clump together efficiently. Dark matter, however, began forming dense regions much earlier. Its gravity created wells that ordinary matter could later fall into, leading to the formation of stars and galaxies. It acted as the invisible framework of creation. But dark matter alone cannot explain the full story. When astronomers measured the expansion of the universe, they found something unexpected. Instead of slowing down, as gravity should cause, the expansion was accelerating. This meant there had to be another force at work, one that pushed space apart instead of pulling it together. That force is what we call dark energy. Dark energy makes up roughly 68% of the universe. It is not a substance in the traditional sense. It does not clump, flow, or gather. Instead, it seems to be an inherent property of space itself, a constant energy that drives expansion. The more space there is, the more dark energy there is, and the faster the universe expands. It is a self-reinforcing cycle that has shaped the cosmos for billions of years. We still do not know what dark energy truly is. Some theories describe it as the energy of the vacuum, others as a new kind of field or force that we have not yet discovered. Whatever its nature, it controls the universe on the largest scales. While gravity binds matter together, dark energy works in the opposite direction, pulling everything apart. The balance between these two invisible forces defines the future of the universe. Together, dark matter and dark energy dominate cosmic evolution. They do not shine, they cannot be touched, but their influence determines how galaxies form, how space stretches, and how time unfolds. The visible universe, the stars, the planets, even life itself, is just a thin layer riding on top of this invisible reality. What we see is the surface of something much deeper. Every observation we make, every experiment we design tries to uncover a bit more of this hidden world. We map galaxies to trace the gravity of dark matter. We measure distant supernovae to track the push of dark energy. Each new piece of data brings us closer to understanding the unseen structure of the cosmos. The more we learn, the clearer it becomes that most of reality exists beyond our senses. The universe is not empty space scattered with light. It is a complex interplay of forces, both visible and invisible, shaping each other endlessly. In the end, everything we know rests upon these hidden foundations. The galaxies shine only because the dark allows them to. In the next part, we'll explore how the universe continues to stretch and evolve under these invisible forces, and how scientists discovered that it is still expanding faster every day. This is the expanding universe. When astronomers look deep into space, they are also looking back in time. Every beam of light travels for billions of years before reaching us, carrying a snapshot of how the universe once looked. What they discovered from these observations changed our understanding of everything. The universe is not static, it is expanding. The idea of an expanding universe was first proposed in the early 20th century. In 1929, Edwin Hubble observed that distant galaxies were moving away from us, and that the farther a galaxy was, the faster it seemed to recede. This relationship became known as Hubble's law. It provided the first solid evidence that space itself was stretching in every direction. To understand this, imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. There is no central point of expansion. The entire surface grows at once. The universe behaves the same way. Space itself expands, carrying galaxies along with it. The galaxies are not flying through space. Space itself is expanding between them. This expansion affects the light we see. As space stretches, the light traveling through it also stretches, shifting toward longer wavelengths. This phenomenon is called redshift. The greater the redshift, the faster an object is moving away, and the farther back in time we are observing it. By measuring these shifts, scientists can map the history of the universe's growth. For many years, astronomers believed that gravity would eventually slow this expansion, perhaps even reversing it someday. But in the late 1990s, observations of distant supernovae revealed something completely unexpected. The expansion of the universe is accelerating. Instead of slowing down, space is stretching faster and faster over time. This discovery led to the concept of dark energy, the mysterious force driving that acceleration. The current best measurements, using data from satellites such as the Hubble Space Telescope and the Planck Observatory, show that the universe has been expanding for approximately 13.8 billion years. It continues to grow larger every second, with distant galaxies receding faster than the speed of light. This does not violate the laws of physics because it is space itself that expands, not the galaxies moving through it. As the universe expands, galaxies that are already far away will eventually move beyond what we can see. Their light will no longer reach us, creating a future where the night sky becomes emptier and quieter. On the largest scales, everything becomes more distant, and the observable universe slowly shrinks from our perspective. The expansion also has consequences for the fate of the cosmos. If dark energy remains constant, the universe will continue to accelerate forever. Galaxies will drift apart, stars will burn out, and eventually the universe will fade into a cold, dark state known as the heat death. If dark energy changes over time, other possibilities exist. A slow collapse known as the Big Crunch, or a violent expansion called the Big Rip. Each scenario depends on how the invisible forces of the universe behave over the next trillions of years. The discovery of expansion transformed cosmology into a science of motion and time. It showed that the universe is not a fixed structure, but a living, dynamic system still evolving. Every second that passes adds more distance between galaxies, more space, and more history. The expansion is not just happening around us, it is happening within us, in the very fabric of the space we occupy. Even now, new observatories continue to measure how fast the universe is expanding, trying to resolve a mystery known as the Hubble tension. Two different methods of calculation give slightly different results for the expansion rate. Scientists do not yet know why, but the answer may reveal something entirely new about the physics of space and time. The expanding universe reminds us that change is not the exception, but the rule. Nothing in the cosmos stands still. Everything moves, grows, and transforms. The same principle that drives galaxies apart also shapes the smallest particles, the flow of time, and the existence of life itself. In the next part, we'll explore how that flow of time bends and slows near massive objects, and how gravity can stretch the very fabric of reality. This is when time slows. Time is one of the most mysterious aspects of the universe. It flows continuously, yet not always at the same rate. To most of us, time feels constant, seconds, minutes, and hours passing in perfect rhythm. But according to Einstein's theory of relativity, time is flexible. It can stretch, bend, and even slow down, depending on speed and gravity. In 1905, Albert Einstein proposed that time and space are connected in a single framework called space-time. Every object with mass distorts this space-time around it. The stronger the gravity, the more space-time bends, and the slower time passes within that region. This means that time does not flow at the same rate everywhere in the universe. Imagine two clocks, one sitting on Earth's surface and another floating far away in deep space, far from any planet or star. The clock on Earth, where gravity is stronger, will tick slightly slower than the one in space. The difference is tiny, but measurable. In fact, scientists have tested this using atomic clocks, one kept on Earth and another flown in an airplane or satellite. Because it reminds us, deep down, that we are part of something larger, something that moves, that endures, that never truly ends. The eternal pulse. Every tide is a breath, every current a thought, every wave a heartbeat. The ocean is not just a place, it's a process, a living rhythm that sustains the planet. And though we may chart its surface, record its sounds, and name its storms, the sea doesn't need our understanding to exist. It simply continues, rising, falling, forever whispering its ancient song to those who are still enough to hear it. In the next and final part, we'll return to the surface to reflect on everything the deep ocean has taught us about life, time, and the fragile beauty of our world. Both realities would be correct. Time itself behaves differently depending on where you stand in the gravitational field. Time also slows when objects move very fast. This is called time dilation due to velocity. According to Einstein's special relativity, as an object approaches the speed of light, its internal clock runs slower compared to one at rest. For example, if you traveled to a distant star at near light speed and returned, you would have aged less than the people who stayed on Earth. This effect, known as the twin paradox, has also been confirmed through experiments with fast-moving particles and precise time measurements on spacecraft. In everyday life, these differences are too small to notice, but they are essential for modern technology. Global Positioning System satellites orbit far above Earth, where gravity is weaker and time flows slightly faster than on the ground. Engineers must correct for both gravitational and velocity-based time dilation to ensure accurate positioning. Without these adjustments, GPS errors would accumulate rapidly, and the system would fail within hours. Einstein's theory reshaped how scientists think about the universe. Time is not a universal river flowing the same for everyone. It is a dynamic part of the cosmic fabric, influenced by motion and mass. Every massive object, from a planet to a black hole, creates its own flow of time, slightly different from every other. On the scale of the cosmos, these variations are profound. Near the edge of a black hole, a second could last thousands of years for an observer far away. In regions with less gravity, time runs faster, letting the universe's oldest light continue its journey to us while billions of years pass elsewhere. The very age of the universe depends on how we define time's passage in different frames of reference. The bending of time is not just a theoretical curiosity. It helps explain some of the most extreme phenomena in the cosmos. It shapes how stars orbit black holes, how galaxies evolve, and even how we measure the history of the universe itself. Time and gravity are inseparable, two parts of the same fundamental structure that governs existence. In the end, time's flexibility reminds us that our everyday sense of now is just one perspective among many. The universe does not keep one single clock. Every star, every planet, every atom experiences its own rhythm, written by gravity and motion. To understand the cosmos is to accept that time itself is alive, flowing differently everywhere, yet binding everything together in one continuous story. In the next part, we'll journey into the most extreme example of this phenomenon, black holes, where gravity becomes so strong that time, space, and even light can no longer escape. This is the edge of time. Black holes are among the most extreme objects in the universe. They form when a massive star collapses under its own gravity, compressing all its mass into an incredibly small region of space. The result is an object so dense that nothing, not even light, can escape its pull. At the center lies a singularity, a point of infinite density where the known laws of physics break down. Surrounding it is the event horizon, the invisible boundary beyond which no information can return. A black hole's gravity is so intense that it bends space-time to its limit. Near the event horizon, time slows dramatically compared to distant observers. From far away, anything falling toward a black hole appears to move slower and slower, its image redshifting and fading as it nears the edge. To the following object, however, time seems normal. It crosses the horizon without noticing anything unusual, yet it can never come back. This strange behavior is a direct result of Einstein's general relativity, which shows that gravity and time are deeply intertwined. There are several types of black holes. Stellar black holes form from collapsing stars, typically a few times the mass of the Sun. Supermassive black holes, found at the centers of galaxies, can contain millions or even billions of solar masses. There are also intermediate black holes, which bridge the gap between these two extremes. Some scientists even speculate about primordial black holes, tiny ones that might have formed in the earliest moments after the Big Bang. The formation of a black hole begins when a massive star exhausts its nuclear fuel. Without the pressure from fusion to resist gravity, the core collapses inward at incredible speed. Protons and electrons combine into neutrons, and the density skyrockets. If the remaining mass is above about 3 times that of the Sun, even neutron pressure cannot stop the collapse. The core shrinks past the point of no return and becomes a black hole. Around the event horizon, matter spirals inward, forming an accretion disk. As gas and dust fall toward the black hole, they heat up to millions of degrees, emitting intense X-rays and radiation. Paradoxically, this makes some black holes the brightest objects in the universe. The process releases vast amounts of energy, sometimes producing powerful jets of plasma that shoot out for thousands of light years. These jets can influence entire galaxies, shaping how stars form and how gas spreads through space. Despite their power, black holes are not cosmic vacuums that consume everything nearby. Objects must pass very close to the event horizon to be captured. Many stars and planets orbit safely around black holes, just as Earth orbits the Sun. The difference lies only in scale and gravity's strength. One of the most fascinating aspects of black holes is the information paradox. According to quantum mechanics, information about matter cannot be destroyed. But anything crossing the event horizon seems to vanish completely. This contradiction between general relativity and quantum theory has puzzled physicists for decades. Some theories suggest that the information is somehow encoded on the event horizon itself, while others propose that it might escape slowly through a process known as Hawking radiation. In 1974, physicist Stephen Hawking discovered that black holes are not completely black. Quantum effects near the event horizon allow them to emit tiny amounts of radiation, causing them to lose energy and, over immense timescales, eventually evaporate. This radiation is unimaginably faint, but it means that even the darkest regions of the universe are not entirely silent. Over trillions of years, smaller black holes will disappear, leaving only faint traces of their existence. In 2019, astronomers captured the first ever image of a black hole's shadow in the galaxy M87 using the Event Horizon Telescope, a global network of observatories working together to act as one giant telescope. That image confirmed predictions from Einstein's theory and offered the first visual proof of an event horizon. It was a moment when theory and observation met, showing that our understanding of gravity could reach even into the most inaccessible regions of the cosmos. Black holes challenge every assumption about reality. They compress space, distort time, and test the limits of physics itself. In their depths, we see how fragile our understanding of the universe still is, and how much remains to be discovered. They are not just cosmic destroyers, but key laboratories for understanding gravity, quantum mechanics, and the true nature of space-time. The edge of a black hole is the edge of time itself, a frontier where all our theories meet and strain against the unknown. Yet even here, in the darkest corners of existence, the same rules that govern stars, atoms, and life still apply. The universe remains consistent, even where it bends beyond comprehension. In the next part, we'll explore what may lie beyond those boundaries, theories about what happens after black holes, and what the ultimate fate of the universe might be. This is the end of everything. The universe had a beginning, but what about its end? Every star, every galaxy, and every atom follows the same rule. Nothing lasts forever. The ultimate fate of the cosmos depends on the balance between gravity, dark matter, and dark energy. Over billions and trillions of years, these forces will decide whether the universe collapses, freezes, or tears itself apart. Right now, all evidence suggests that the universe is expanding at an accelerating rate, driven by dark energy. This means that distant galaxies are moving away from us faster and faster, and one day they will disappear from view entirely. As space stretches, the light from those galaxies will redshift until it fades into darkness. Eventually, only the galaxies bound together by gravity, like our local group, will remain visible. In about 5 billion years, our sun will exhaust its hydrogen fuel and expand into a red giant. It will engulf Mercury and Venus and possibly Earth before shedding its outer layers. What remains will be a white dwarf, slowly cooling over trillions of years. Other stars will follow similar paths, fading one by one until the galaxies lose their light. Over even longer timescales, star formation will stop altogether. The gas clouds that create new stars will be used up or scattered. The universe will enter what scientists call the degenerate era, when only remnants remain: white dwarfs, neutron stars, and black holes. The night sky will be almost completely dark. Trillions of years later, even white dwarfs will cool to become black dwarfs, cold, dead spheres no longer emitting light. Galaxies will drift apart, and their stars will fade into invisibility. Matter will continue to decay, and the universe will grow colder and emptier with time. This slow fading is sometimes called the heat death or big freeze. In this scenario, the cosmos never truly ends, it just becomes eternally still. But there are other possibilities. If dark energy changes its strength over time, it could reverse the expansion or accelerate it beyond control. In the Big Crunch theory, expansion eventually slows, stops, and reverses. Galaxies would move back toward one another, and the universe would collapse into an incredibly dense state, perhaps triggering another Big Bang. In the Big Rip theory, dark energy grows stronger, tearing apart galaxies, stars, planets, and eventually atoms themselves, leaving only isolated particles in an ever-expanding void. There is also the possibility of quantum decay, tiny, random fluctuations that could one day trigger a vacuum collapse. In this case, the universe would suddenly transform into a lower energy state, rewriting the laws of physics instantly. Everything we know, including atoms and light, would vanish in a fraction of a second. This scenario is purely theoretical, but it reminds us how little we truly understand about the fabric of reality. Whatever the ending may be, the universe's story is one of transformation, not destruction. Every phase gives birth to the next. The atoms in your body were once inside a star. The light you see tonight began its journey billions of years ago. Even in its distant future, the universe will continue to evolve in ways we cannot yet imagine. Some scientists suggest that black holes might hold the key to renewal. As they evaporate through Hawking radiation, they could release the final energy of the cosmos, filling space with a faint glow. In that quiet light, new physics might emerge, perhaps the seed of another universe, restarting the cycle once again. The end of everything may not be an ending at all, but a transformation beyond our comprehension. The universe began in darkness, found light, and may one day return to stillness. Yet, through all its changes, it follows the same timeless rhythm of creation, expansion, and renewal. In the next and final part, we'll look at how this vast story connects back to us, how we, tiny observers on one small planet, are part of the same cosmic evolution. This is the universe within. Every atom in your body was forged in the heart of a star. The carbon that forms your cells, the calcium in your bones, the iron in your blood, all of it was created in nuclear reactions that took place billions of years ago. When stars died, they scattered these elements into space, where they eventually became part of new stars, planets, and life. You are, in the most literal sense, the universe made conscious of itself. For a long time, humans thought of themselves as separate from the cosmos, small observers watching a distant, infinite universe. But science has revealed something different. The same laws that shape galaxies also govern the chemistry of your brain. The same gravity that binds planets together keeps you on the ground. The same light that travels from ancient stars touches your skin every day. You are not outside the universe. You are an expression of it. The atoms in your body are billions of years old, recycled countless times through stars, dust, and worlds that no longer exist. Every breath you take contains molecules that once passed through ancient oceans or drifted in interstellar clouds. Even your thoughts, the flow of electricity through neurons, are guided by the same physical principles that power stars and lightning. The boundary between you and the cosmos is an illusion created by perspective. When you look up at the night sky, you are looking into your own history. The light from distant galaxies began its journey long before Earth existed, yet it reaches you now, connecting past and present across unimaginable distances. That light carries the story of everything: the birth of atoms, the rise of stars, and the creation of life. In a way, you are that story, written in living form. Our understanding of the universe is still incomplete. We do not yet know what dark matter is, why time flows the way it does, or how consciousness emerges from matter. But the fact that we can even ask these questions is extraordinary. It means that the universe has evolved to a point where it can study itself through us. Every discovery we make is the cosmos learning a little more about its own nature. From the first particles after the Big Bang to the vast networks of galaxies stretching across space, everything is connected. There is no separation between the distant and the near, the large and the small. The same physical constants apply everywhere, binding the infinite and the intimate into one seamless whole. The universe is not just out there, it is also within every heartbeat, every thought, and every moment of awareness. In time, our species will fade, like all things. Stars will die, galaxies will dim, and the universe will move toward whatever fate awaits it. But for this brief moment, we exist. We can see the stars, understand their light, and feel awe in their presence.